Hello and welcome to the Cyber1 YouTube channel. My name is Ray, and in this video we're looking at the RoboHAT again, and this time the INA219 chip. Now there are actually 8 INA219s. They are on the servo output board and they're located across the top here. These chips are a high side current monitoring chip that will measure both positive and negative current flows. In this case, we're only using it for a positive current flow, and what we've done is using the PCA 9685 to drive up to 16 servos. We've taken those as pairs and we're running the current of 2 servo motors through one load resistor located at this point here, and we're just looking at the voltage drop across that load resistor to see how much current is being drawn. Now this chip is not as complicated as you might think. The most complicated part about it is doing the maths to get the amps that is actually being drawn by the motor. So I've hooked up 5 volt to the terminals here, which is the servo power, which supplies power to the top of all of those chips, or those resistors, and the bottom of the resistors feeding pairs. Now this board does have located between each pair of resistors these little pads. There is a shorting link between the center pad and the top one. You can cut that shorting link and then put a solder bridge on the bottom pair, and that'll put 3 of these pins on the first one and the 4th one onto the second chip on its own for current monitoring. So you can split it 3-1, 3-1, 3-1, etc., or leave it as pairs. So let's have a look at the code. We're starting with the input SM bus 2, and we also need time because we're putting a time delay on this so that we can actually read the values coming back. The device address, these chips, you can only have 8 of them max on an I2C bus without using a multiplexer, and I haven't got a multiplexer, so I've got 8 on there, and they are in the address range of 40 hex through to 47 hex. And if you remember, we do have the 2 ADS 1115 starting at 48. So this fits in quite nicely. We have a user configuration value. This is a constant that I'm using. Essentially, this is a bit field where different bits mean different things. So bit 15, for example, and I've listed these in the example code. Bit 15 is reset. 14 is not actually used by the chip according to the data sheet, so we always leave it as 0. We have the bus range is the next 2 bits, and so we have a 1, a divide by 2, divide by 4, and divide by 8, which gives us our millivolts across the resistor. This is the maximum millivolts we're likely to see, and I discovered that it doesn't really give us any real benefit setting the higher gain. So we'll be running it using a gain of 1. The ADC, or analog to digital converter, there's 2 sets of settings. One is for measuring the battery voltage or the supply voltage, and the second one is for measuring the shunt voltage. Now what that is because this is a high side reading, we're actually going to measure what our supply voltage is, and then we're going to measure the shunt resistor voltage drop. So one will be in volts and the other one's going to return in microvolts. But we can sample at 9-bit, 10-bit, 11-bit and 12-bit, and it also gives us the conversion time, how long it takes to actually read that amount. We can also do oversampling, where we read it 2, 4, 8, 16 32, 64 or 128 times and average that, which allows us to get a higher accuracy at the expense of time. So this is working in milliseconds or microseconds if you go to a single reading at a lower bit rate. We also have the operating mode. The operating mode is set here. So setting an operating mode of 0 will turn it off, so power it down. We can read just the shunt voltage, we can read just the bus voltage, or we can read the shunt and bus voltage on a triggered or on a continuous basis. So that's just something to keep in mind. We'll be using the shunt and bus triggered. Now there's two configurations for the way the ADC. It's got a single analog digital converter built into the chip, and so it has to switch whether it's measuring the battery voltage or whether it's measuring the shunt voltage. And by using the shunt and bus triggered, it will automatically read one, then change, and then read the other, and then return the two values for us. Alright, so registers, cal value. Cal value is something that I will come back to. It's a calibration value, and then we've got R shunt and max amps. Now max amps is the maximum number of amps that we are expecting to see through the shunt resistor. And if you know the value of your shunt resistor, which is R shunt, and in this case it's 0.005 ohms, then you can calculate the microvolts or volts that you're going to see across that shunt at 10 amps. So in this case, you'd be looking at 10 microvolts or thereabouts. We have this calibration value which we use to multiply against, or we tell the chip to use to multiply what it's receiving as to give us a value back, and then we can use that same calibration value to actually convert the value we're getting back into microvolts. Alright, so let's have a look at some of the setup. We are going to calculate CLSB. So CLSB is it's a calculated least significant bit value. So max amps divided by 32,768, which is half the maximum value that this thing's likely to return. Now remember that the maximum value that we can get on a 2-byte value is 65,536. Because this is able to return a negative current flow, then you have to basically divide that by half to get our negative values. Cal value here is using a constant that I calculated out based off the data sheet, divided by the CLSB, which is our least significant bit constant, times the R shunt to get this cal value, and then I totally ignored it, I think, until later on. Yep. User config, I worked out what we needed, worked out what bits we needed, and I converted it into 2 bytes. And that's because it's a 16-bit value, but we have to write them as 2 bytes. And there is another way I could have done this, and I will probably change the code to reflect that later on. Then part of our setup, we will write the configuration register using the I2C block data. So we send the device address, in this case it was 0x40. We send the configuration, which is this value, this value here, 00, and we send the user config, which we have here. We then write the next one, which is the calibration, and we take the cal value that we calculated out here, we split it into the two separate bytes. Once we've done that, data bus read, so we can read the configuration back. In this case, I am reading it back. This was part of my diagnostic to make sure the code was working, and we will read back what was actually programmed into the configuration. And we do the same for the calibration, just to confirm that the calibration value was written, and I will write out both the calibration and read back what was saved. And then we go into our loop. Now the loop is going to read, we're going to look at data valid for a start to make sure that the data we're getting back is valid, and there is a way of reading that. There is one bit in particular that is not set while it's reading and is set when the data is valid. So we'll measure the bus voltage and the shunt voltage in this case. In a later bit of coding that I will working on, which is the driver set for the RoboHAT, it will have a series of classes, and in those classes we're not actually going to bring back the shunt voltage. We don't actually need it. We do need the voltage, we do need the current, we do need the power, which it will calculate for us. So yeah, we'll read back in. We're going to convert those into their appropriate voltage using, in this case, S volt divided by 100, and we've got bus read for the bus voltage, and we will convert that as well. B data is this is our conversion to 16-bit, and we multiply by this value to get it to where we need it. If B data, so that's our bus data voltage, and 1, so that's the very first bit, is equal to 0, then the data is valid. If it's equal to 1, it's in the middle of a conversion, and so we're not going to print that, and we'll just go through the loop again. A data is our analog data, amps data, sorry, coming back when we read the current, and we take amps is equal to A data times, the first one's multiplied by 255, which is essentially a left shift. I could have left shifted it and it would also have worked by 8 positions. We add in A data 1, which is the second byte, which is a low byte. Multiply it by CLSB that was calculated earlier. So CLSB is max amps divided by 32,768. And that gives us our amps, and then we do something similar to get multiplied by 20 down here to get our watts, and then we just print it all out, formatting it so it's easy for us to read, and we'll wait a second before we go through and repeat that. We can actually run this a lot faster. I can run it at 0.1 or 10 times a second. So let's run this code and see what we've got. For the hardware side, I've got a small servo. This is a JX servo 5521MG-180, so it's a 180 degree servo. I'm running this at 5 volt, and it's on port 0, and that's what I'm reading from. If you actually look at the wiring diagram for this, 0x40 is port 0 and 1. So let's run this and see what we get. And you can see here I've got 5.096 volts. Now my voltmeter on my power supply only goes to 1 decimal place, and it's showing 5.1, which is close enough. If you do rounding, you get your 5.1 volt. And it is slipping up to there from time to time. The next one I'm showing is the shunt voltage, and that's how many millivolts is on the shunt voltage resistor. And as you can see, it's not much. We're talking microvolts here, so 0.12 milliamps. Sorry, millivolts. The next one is the amps flowing through. Now, according to my power supply, I'm getting between 0.024 and 0.027 amps, and you can see here that's pretty close. It's reading 0.26 and 0.24, and there was a 0.03 there. And that converts it then next into the watts, which is again in the milliwatt range. So we're looking at 150, 120 milliwatts. Now, if I apply a little bit of a load to our servo, you can see the current will rise up, and we've increased our milliwatt power going to it. When I take the load off, you can see it drops back down. And what you're seeing on the display is very similar to what I'm getting on my power supply. And we're down to 0.008, or my power supply saying 0.010. So it's actually showing exactly what we want. The last information was S data, so that's actually what we're getting from the shunt when we're reading the shunt data. And you can see the shunt data at the moment is very low. So we're only talking, 4 or 5 multiplied by our value. So we're not, when I move this, put a bit of load on, you can see that value gets bigger. So why did I include this one on the RoboHAT? And that's mostly for a robot that is supporting its own weight. We can actually measure the load on the legs. How much power are the legs actually drawing at different points? When the robot is supporting its own weight, in the case of the Spot Micro robot, that current will increase. And so we'll be able to see when a foot is on the ground supporting weight. So that's the major reason for the inclusion of this chip. Well, that'll do for this video. If you like these videos, don't forget to click on like, subscribe, and ring that notification bell. It's a form of support that helps the channel a great deal and costs you absolutely nothing. If you'd like to support the channel further, I do have a Patreon account, and you can join my VIP patrons Go Lucky and Copernicus, my All Access patron Jeff Jerd, my Builder patrons El Morales 45, Andrew Cardone, Airgar69, and Stefan Paps in supporting the channel. I also have YouTube membership, so you can join through that method as well. All my patrons get these videos around about a week early. If you've got any questions, feel free to leave a comment below, or drop into my Discord. There will be a link in the description, and you can ask your question there, and if I can't answer it, someone else might be able to, but I'll do my best to answer it. And we'll see you in the next video.